Okay, so what you'll be doing is in one of your next assignments, and I put the detail on the web, but let me just explain the idea. So you'll be doing MNIST digit classification by creating a matrix form of the neural network that we just described. Okay, so MNIST is a data set where what we have is we are given pictures of digits 0 through 9. Okay. Okay. Each is 28 by 28 pixels. So these are grayscale images. So suppose the value here is 30. Value here is, in the first row, last value is 81, and the next value over here is 45. So if we assembled it into a vector, what will happen is we'll start writing all these numbers, 30, 81, then we'll go to the next row if the first value is 45, right? So we will basically come up with one vector for all the pixels in one image. Okay, and if you take a look at what will be the size of that size of that image will turn out to be 784 by 1. Why is 784 by 1? 28 by 20. Right? So basically that will be your input x to your neural network. Okay? So this x, as you can see, is now a vector 784 by 1. Right? So what will happen is then, let's say, this is the picture I was looking for on my computer. So let's say we wanted to use 100 neurons over here. So 100 neurons in the hidden layer, right? So can you tell me what will be the size of this matrix then? 784 by 100. So this weight matrix over here will be 784 by 100, right? Okay, so then let's say we further go over here.
Should be 75 bias.
Biases we are added, they are not part of the multiplication of the weights. Okay, so then let's say now we go over here. In the very last layer we have 10 neurons. Why 10? Because there are 10 classes, so it has to be 10. Okay, so if I call this W1 matrix, if I call this W2 matrix, what will be the size of the W2 matrix?
100 by 10.
100 by 10. Okay, so now as we go and describe the loss over here, right? So there are 10 inputs over here for each. So for example, let's say we feed in digit 3. If we feed in digit 3, in the beginning all the weights are initialized randomly. So the 10 outputs over here might be 0.11, 0.91, 0.37, 0.65, right? So this will be A will be 10 by 1, the actual outputs. Okay, the Y, which is the expected output. If it is 3, what will it be?
0, 0, 1, everything
0,
0.
0, 0.
You start with
So this is for 0, this is for 1, this is for 2.
Then for 3 should be 1.
3 should be 1. And the rest will be 0. So this will be our expected output, right? So then we'll define the loss function. Okay. So if you review, I'll give you the starting code for some of these. If you review, the nice thing is NumPy library in Python is extremely easy at multiplying matrices. So if you just do, if you had a W matrix, you multiply it with, you simply say W times X, or you can do NP dot dot, either way. So it can easily multiply matrices. Okay, so as we train our system in this MNIST digit classification, there are 50,000 training images, meaning you're already told what that image is, whether it's a 3 or a 4 or a 5. There are 10,000 test images. So after the network is trained, we'll fix the weights and the biases. Okay.
Do we really need all 50,000 to train it?
If you were writing a research paper comparing it with other people, you'll use exact 50,000. But a lot of you have, laptops that may, take a long time for it to train. So what I've done is in the assignment, I have created a subset of 1,000 of these for training, so that very quickly you can train it. But you will test it on the still 10,000 to see how good it is. Okay. So anyway, just a couple more minutes. Let me clarify the assignment so that as you see it, you will know what you need to do. So in the beginning, you will initialize the weights randomly and the biases randomly, right? You'll pick one training sample, you'll pass through it. As we discussed, some will be W times X plus B. B is also initialized randomly. Then this sum over here will be W2 times whatever the output here is, plus B. And so once we know the outputs, we can do the subtraction with the expected output, take the square, and compute the loss, right? Then as we work backwards, like I said, we will need to compute the deltas first. So for example, what would be the delta over here? Okay, as we discussed, that's easy. That's a derivative of the loss with respect to the actual output. So which is basically 2AI minus yi, or I is the training data. So A is a 10 by 1 vector, Y is a 10 by 1 vector, right? Sometimes in the loss, we put the half over here so that we don't have to keep multiplying it by 2 when we take the derivative, right? Okay, anyway, as you compute partial L over partial A, next is partial A over partial S over here, which again will be very easy. That will be A times 1 minus A, correct? Whatever this A was. Okay, once we have the deltas, how do we compute the deltas over here? Okay, so let's take a look over here. This is, what's the size of this
That's
delta?
10 by 1.
That's 10 by 1.
We do the same thing but with the W now. So it's
Okay.
W times that.
Over here, this is 100 by 1, right? So as you can see, if you just did a multiplication, you'll get 100 by 1 easily, okay? So anyway, so you will do matrix multiplications. You will see how much accuracy you're getting as you write the code. I'll give you a lot of starting code that you will play with, get better at it. Anyway, so look for this assignment, and I will stop here today.